Hello, we are the team named Max, and we will introduce you to our half-turn challenge. The project scope is to control the speed of a DC motor managed by an external computer, microcontroller, and a motor drive. To accomplish this task, we should establish at least three nodes in rows, one for the input, one for the controller, and one for the motor to enable the correct communication between nodes and topics. First of all, we decided to use the waterfall methodology given our prior experience in the previous challenge. This establishes a clearly defined sequence of execution of the project phase, where all the team members collaborate at the same pace, ensuring that we only advance once the phase receives a final approval. We started the project with investigation of an equations table for our system. Since we are working with a discrete system using PWM on the Arduino, it cannot be treated with a typical PID controller. Therefore, it's necessary to employ the C transformation, as we can see in the right image. For the next step, we tested the following hardware: the Arduino Mega, H-bridge, and a 12-voltage motor with an encoder that will run at 30 revolutions per minute.
We sent a maximum input from the PWM to our program, and we monitor its behavior over time using the encoder signal. To measure the encoder signal, we utilize the following Arduino code. This code was designed to capture interrupts and requires a specific pin. In our case, we use pin 3 on the Arduino Mega, as we can see in the next table. We conduct a test to capture the motor behavior, printing results every 0.01 seconds on the Arduino serial monitor. These results, ranging from 0 to 255, were easier for us to understand. This revealed that the maximum speed achievable with our H-bridge was around 24.5 revolutions per minute, as it couldn't output a precise 12 voltage. The motor exhibited a rapid response, stabilizing quickly, requiring only a limited dataset for analysis. And we can see in the table below the results.
To calculate the transfer function, we perform three different steps. To start with, in step 1, we input information returned by the encoder in the MATLAB workspace and run the ident function. After that, we import the information on the screen and then click on estimating a process model function. Finally, we verify that it matches at a less 75% of our function. On the other hand, in decision-making, using MATLAB transfer function, we now employ MATLAB control system toolbox to calculate our constant based on how we want our system to behave. To do this, we execute the PID tool function, input our function, and finally, the constant we selected resulted in the following PID system. The constants that best fit are the ones displayed on the screen.
So now I'm going to talk about the communication in our system. We use three nodes: the setpoint node, the controller node, and the Arduino serial node. We also use a launch file, and we create a folder for custom matches for setpoint node. The controller node receives the setpoint, do the PID control, and send the signal to the Arduino serial node. And the Arduino serial node receives the input, this to control the motor rotations, and send back the output to the controller node. And in the next video, we can see how our system works. We send different values for the set point, and you can see that it works fine. And interesting that you can see is that we use RPM, but with the conversion, it could be perfectly radians per second. And in the next video, we can see how our system works. We send different values for the set point, and you can see that it works fine. And interesting that you can see is that we use RPM, but with the conversion, it could.
Now, as conclusions, we can improve the quality of the hardware, find external libraries to improve the controller system through Python and Rust, find a more powerful microcontroller like a Jetson Nano to seek a live analysis and a correction of the system, and encourage to keep learning to code to make our system faster and efficient.